Okay, first of all, kinetics. Why do we need kinetics? To fully understand a chemical reaction, we must understand its stoichiometry. Remember, stoichiometry is used in chemistry for everything. In the AP exam, most all problems will have a stoichiometry problem. I know that you are very related to stoichiometry. The energetic is if it's exothermic, endothermic, how much energy you need, but also rate. Rate is very important, and that's what chemical kinetics studies, the speed or rate at which a chemical reaction occurs. Why is this important? It is important because we must understand the rate of reactions to know if the reaction will be explosive, and we need to take some precautions. Or if it's too calm, that we won't see any effect. Especially, we want to make money. We might to produce the products for any profit. Then we need to understand how long will the reaction will take place. For example, reactions like in fission, the initial steps in fission take place at 10 to the negative 12 of a second, so almost instantaneously. But for example, the conversion of graphite to diamond take millions and millions of years. For example, a reaction that is used in the industry to produce ammonia for fertilizers at 25 degrees shows no reaction. But even though this is a reaction that is used for profit and it is used worldwide in many industries. So if we understand the rate of reaction, then we can actually make a profit and benefit from the reactions. Okay, so reaction rates. If we consider a simple reaction of a reactant to give a product, reaction rate can be expressed as the reactant will disappear. That's why we'll have a negative. So the change of concentration of the reactant, the disappearance of the concentration of the reactant over time, that will be the rate, or how fast the product will be formed. So the change of concentration of the product divided by time. So in this graph, what we can see is we have the reactant that will start here at 40 molarity. It could be whatever concentration. And of course, the product will start at 0. In the beginning, you won't have any product. As the reactant starts decreasing, of course, the product will start increasing, right? And the rate of reaction is how fast the reactant decreases its concentration and how fast the product is formed. Does this make sense? So for example, if we use stoichiometry for the reaction rates, in general for a reaction where the lowercase letter will represent the coefficient, the stoichiometry coefficient, and the capital letters will be the substances. So in this case, we have A and B as reactants and C and D as products with its proper coefficient. The rate expression is given by the reciprocal of the coefficient, and again, the rate of the change of concentration to the change of time. Notice how the reactants are negative because they're disappearing, right? You have less reactant each time as time passes, and the products are being created. That's why they are in positive values. Okay, for example, let's practice this concept for now. For this reaction, suppose that at any particular moment during the reaction, molecular oxygen is reacting at a rate of 0.042 molarity per second. Write the rate expression for the reaction. At what rate is dinitrogen pentoxide formed, and at what rate is nitrogen dioxide reacting? So the rate expression, we're going to have, remember, the reactants are negative, so the reciprocal of the coefficient, 1/4, negative 1/4 of the change of concentration over change of time of NO2 would be the same as the rate in which oxygen will be disappearing. Since we don't have a coefficient, we just place a negative change of concentration of oxygen over change of time equals 1/2, because the coefficient is 2, the change of concentration of N2O5 over change in time. Notice how this is positive, these two are negative. Questions here? Okay, I'm going to continue. So now, letter B, at what rate is N2O2 being formed? So the information that they gave us is that oxygen is reacting at a rate of 0.042 molarity per second. This one, we are going to add the negative because remember that the reactants are decreasing with time. So if we get from the rate expression, considering only oxygen and dinitrogen pentoxide, and then we solve for the change of dinitrogen pentoxide over time, then we will have to multiply the rate of the one that they gave us of oxygen times 2 times negative. Well, we pass the 2, we have the negative here. So we will have that dinitrogen pentoxide is being formed at a rate of 0.084 molarity per second. Remember to consider your sig fix, and that will be our answer. All good here? Any questions? Hi, Greta. Okay, let's move on. So now, letter C, hi, Fer. Letter C, it says, at what rate is NO2 reacting? So again, we're going to, get it from the rate expression, right? What should we do with this rate expression? What do you think we do? What math equation are we going to do now? If we want to solve for change of NO2 over change in time, what must we do with the rate of oxygen? Multiply by what number or divide by what number? Correct. Multiply times 4. Correct. Multiply times 4. If we see here, the negatives cancel out, and then we pass only the 4, but this is still negative. So we will end with a negative value, which makes sense because NO2 is also a reactant. Now, we don't need to, in our sentence of the answer, we don't need to say, yes, Irene, it's like cross multiplying. Correct. We can give our answer as saying that NO2 is reacting at a rate of 0.17 molarity per second. Or we can leave the negative, whichever way it's correct. Okay, so now we're going to go with the rate laws. There's 2 rate laws. We have the differential rate law, which is called rate law only, and we have the integrated rate law. We're going to see both of them today. For this reaction, again, remember, lowercase means coefficient, capital means the substance. For this reaction, the rate law will take the form of a constant, a rate constant times the concentration of the reactants to the power of a number, of X and Y. Important points to consider in this rate law is that we are not in, yes, K is a constant. Yes, Dakota. K is a constant, correct? The concentration, we're only going to consider reactants, never products in kinetics. Why? Because we are going to study the reactions under conditions where the reverse reaction won't contribute that much. We already know that some reactions are reversible, but for kinetics, we're going to study the kinetics only when the forward reaction takes precedence over the reverse reaction. So that's why we only use reactants, never products in kinetics. And X and Y are not the coefficients. X and Y, we need to, it's going to be determined experimentally. So in the exam, in the problems, you're going to see data received from experiments. for you to get the X and the Y. We're going to practice in a moment. Okay, the overall reaction order, which is also a common question, is the addition of the exponents, X and Y. Okay, and the exponent itself is the order of reaction of the specific reactant, as we're going to practice in a moment. Okay, for example, that's what I was saying about. They're going to give you a set of data where several experiments, where you start several experiments with specific concentrations of reactants, and they're going to give you the rate of the initial rate of that reaction. So for example, here we have 3 experiments with different concentrations of the reactants. We ignore C, the product, and we're going to see how to solve these equations. So a common method is to study those data from the experiment. If doubling the initial concentration of a reactant causes the initial rate to double, then the reaction will be first order in that reactant. Okay, Paula, they're going to give you, will they ever give concentration or rate in a table like that with concentration at a time other than 0? Okay, Perla, those kinds of problems are going to be with the integrated rate law, where time comes into place. There's 2 rate laws. This one is the differential rate law, where you consider only initial rates. And the other method, which we're going to talk about in a moment, is the one that gives you at different times. We're going to see it in a moment, that concept. Okay, in this case of the initial rate, yes, this is the initial concentration zone. Okay, so as I was saying, you're going to check the how does the initial concentration varies, and that variation, what is the cost on the rate? Again, if you double the initial concentration and the rate doubles, then the reaction will be first order. If the initial concentration doubles and the rate quadruples, then the reaction will be second order, and so on. If we double the concentration, causes the initial rate to increase 8 times, then it would be third order. If doubling the reactant does not change, then it will be order 0. So we're going to see some examples. So let's go back to the same example. If we look at experiments 1 and 2, we're going to notice that the concentration of A doesn't change, and the concentration of B doubles. We need to go and check the rate. The rate doubles as well. So what would be the order? What would be the rate for B in this case? Yes, Fernanda, it would be rate 1. Correct, correct. With the exponent of B would be the first exponent 1. Correct, Carmen. Yes. Then we need to check for 2 experiments where now the concentration of A changes and B is maintained constant. So if we observe experiments 2 and 3, in here B is constant and A doubles. So this one doubles, but the rate quadruples. So what would be the order, the rate for A? Exactly, exactly, very good. So the rate law would be concentration of A to the power of 2 to second order in respect with A, and first order in respect with B. And remember that the addition gives you the overall order, so it would be for third order, this reaction. Okay, Fernanda, what you mean is if, okay, I'm going to answer Anika's question first and then first. Okay, what you do is you try to choose experiments where one is maintained constant and only one changes. So for example, If B in experiments, if we only observe experiments 1 and 2, we check that concentration B doubles while A is maintained constant. So we check the rate and the rate doubles, but this effect will only be with respect with B. So that's why it's order 1. And then we check experiments 2 and 3. Why do we choose to check those two? Because now these two are constant. B is not taking any effect on the rate, only the doubling of A. So now this change of rate will be only considering the doubling of A. Does this make sense, Anika? So you first look at experiments 1 and 2 to check for B, and then 2 and 3 to check for A. Okay, now, Fer, if you check, if sometimes they give you where every time there is a change, for example, suppose that this one goes from 0.2 to 4, and you already know that this one's order 1. So if this one changes, for example, if here we had a doubling as well, if here we had 0.80, for example, then you check, you take in consideration the other rate that you already decided. Exactly, Harman, exactly. If you already know the concentration of one, then you can get it, you consider that power to get to the other one. Okay, now, the value of K, you can get it since you already know the rate of each reactant, then you can get the value of K with any row, with any of the experiments shown on the table. Since you already know that the rate is the constant times the concentration of A to the power of 2 times the concentration of B, then you can solve for K, use the values of any experiment, and solve for K. And be aware of the units. Yes, Anika, I do have another one. Questions for this problem, for this one in particular? Okay, we're going to move on with the next example. Okay, yes, just a reminder, an easy way to remember or to determine the values for K is this simple equation where K would be L to the liters to the X over mole to the X times time, and the value of X will be 1 less than the order of the reaction, by the overall order of the reaction. So if the reaction is third order, the values of K will be liter squared over mole squared times time, and so on and so forth, the second order. So this is an easy reminder for you to know if you're on the right track. Yes, I'll share with you the slides where they're already shared in the, but I'll make sure they're shared once I finish the stream. So if you can review this again, if you want to review this again, you can check it on the slides, or you can take a photo right now to your screen. Yes, this one helps a lot. It's very useful. Correct. Okay. So another example, now with an actual equation. In this equation, if we have ammonium ion and nitrite ion gives you nitrogen gas and water. Again, they're giving you several experiments, and these are initial concentrations and initial rates. So if we observe experiments 1 and 2, the only one that is changing is the concentration of NO2. So this is doubling, and the rate is doubling as well. What is the rate with respect to NO2? NO2 minus. Exactly. Now, if we observe the other two experiments, where now the one that is doubling is NH4 and the NO2 is maintained constant, now we check what happens to the rate. And the rate, as you can see, also doubles. So what would be the rate with respect to NH4? Correct. Again first, and what would be the overall rate? What is the overall rate? Correct. It's second order, correct. So yes, you got this. Excellent. Okay. Yes. Now, if we want to get the value of K, again, as we did before, we are going to get the values of any experiment that you want. So you choose any row and you plug in the values here and solve for K. Now, remember the key that I told you on the last slide? What would be the order of K for this in particular? Okay, I'm going to repeat my question. For K, you're going to substitute the values for any experiment. But what would be the values, the units for K? Exactly. So if we if we solve for K and we plug in the values of any experiment, then we're going to get the answer, and the units is going to be liters per mole times seconds. Okay, any questions in here? No, right? Okay, we're going to move on. Okay, now we're going to see the integrated rate law. This is the one that takes time in consideration. Thank you, Perla. Okay, the integrated rate law expresses how the concentration of the reactants change over time. So in this case, we are changing, we're going to use one experiment and check how the concentration of the reactants decrease over time. So instead of having several experiments with initial concentrations and checking the rate, we're just going to do one experiment, or the data is going to come from one experiment where we're going to check concentration and time throughout the experiment. So for example, if the overall order of the reaction is first order, we're going to see first, second, and zero order. We're going to start with first order. So if we have a simple reactant, a single reactant A that turns into B, the rate law would be that the concentration of A decreases over time, or the constant only depends on K to the power of 1. If you do integration to this equation, this is what you're going to get. Yes, Perla, the graphs apply only to the integrated rate law. Yes, that's what we're seeing right now. Okay, so correct, concentration versus graphs versus time. Is it, okay, Annika, let me show you again the screen of the, okay, this is what you're asking, Annika? Yes, this is a great key to make sure you're doing the right calculations for K. So again, this is going to be shared with you. This presentation is going to be shared. Or if you want it right now, you can take a photo of your screen. And this is really a fast and easy way to check your work. Okay, we're going to move on. So as I was saying, the integrated rate law. Okay, in a moment, we're going to talk about molecularity. Perla, it's nice that you studied and you have all the concepts like this. Very good. Very good. Thank you, Perla. We're going to talk about, well, in fact, Perla, molecularity, we're going to see it on the next stream, next week, because that has to do with reaction mechanisms. In this stream, we're not going to touch reaction mechanisms yet, because it's first the introduction. Okay? Okay. So let's continue. So the integrated first order would be this one. If we integrate this equation, this is what we're going to get. And now you're going to have the natural logarithm of the concentration of A equals negative K times time plus a natural logarithm of the concentration of A, of the initial concentration of A. This equation shows how the concentration depends on time. And if we know the initial concentration of A and the value of K, then any other concentration throughout the reaction can be calculated. If we notice, this equation has the form of a line, right? Because the straight line has the form y equals mx plus b. And if you look at I match the colors, this will be y mx plus b. So if you have a graph, or if you plot the natural logarithm of the concentration of A versus time, then you will have a straight line. And this is very useful because then it's very easy to get the slope, which, as you can see, would give us the value of K. Okay, so for example, an example of first order reactions. They're going to give you data from an experiment. So in here, they give you the data of the decomposition of dinitrogen pentoxide. And in this case, they're asking you to determine the rate law, the integrated rate law, and the value of the rate constant. Now, we don't have the initial rate, so we cannot do the other method. The other method of the differential rate law is when we have several experiments with the initial rates. So that is a hint of that you're dealing with the integrated method. Okay, so what are you going to do? You're going to graph the values. And as you can see, this doesn't give you a straight line. So what other thing that you can do is to do the natural logarithm of the concentrations and then graph that. And as you can see, now we have a straight line. So now the straight line with a natural logarithm, it's an indication that this is a reaction in first order. Does this make sense? Okay, now this graph, you can do it very, very easily. I know you all have a graphing calculator. And you can do the graphs in your graphing calculator. Yes, Irene, like trial and error. Yes, you plug it into the calculator and you can plug in the first column. If it doesn't give you the straight line, then you can do it. The calculator has the values, remember, on the chart. So you can very easily plug in the calculation. You don't need to do it on your own, the whole column. If you place that you need the natural log of this column, the calculator will do it on its own. So you can do it very, very fast with your graphing calculator. So now that you identify that the straight line is given by the natural logarithm versus time, you already have the order of the rate law. So now you can do the first two. Exactly, Fair. Plug in all the data, all the information to a new sheet of data in statistics, and it's very easy to now choose the graph. Remember that in the graph you can choose the values that you want on each axis. So it would be very easy to placing the values, typing the values only once, only of the concentration. You can very easily calculate the other. Exactly. So once you decided that is order one, then it's very easy to determine the rate law, right? Because it's order one, and the integrated rate law. How can you get the value of the rate constant? How can you get the value of K? Exactly. Remember that this is the formula of a line. So yes, this would be the, yes, very good. Thank you, Perla. So we remember that the value of the rate constant will be the negative slope. So you can get the slope with your graphing calculator, or calculate it with the formula for slope, which, as you remember, is change of y over change of x. So you can do it with the values that you got from the graph, from your graph of the natural log. I'm sorry, these values, right? So you can choose two values from here and two values of time, just as you do with any slope calculation. And the slope is negative, but then your K would be positive. Any questions on how to get the value of K? Okay, now in letter B of the problem, they ask us what would be the concentration of dinitrogen pentoxide at a specific time. And remember that we can do it with the equation. With this equation, now we already have the values of K. We do have the values of this one, again, from the table that you got, that you changed your concentration to the natural log. That's where this 0.1 comes from. The 250 is your time, and the K that you calculated. So the natural log is negative 4.04, but you need to do the anti-log, right? Because you don't want the natural log as the answer, you want the concentration. So you do the anti-log and you get this value. And if you compare, remember that it's very important always to check your work to make sure it makes sense. So if you check the initial concentrations, it makes sense if you are in time 250 seconds, it makes sense to be in between these two numbers. Steady state approximation, again, that's for next stream. This is Kinetics 1, the introduction, and Kinetics 2 will be next week, again on the Wednesday. Okay? Okay, so now they can also ask you in these kinds of equations, they can also ask us to calculate half-life. So if they tell us to determine the half-life of N2O5, we have two ways to do this. One way, half-life, as you can remember, is the time required for the reactant to reach its half of its original concentration. For first order, the half-life for first order reaction is constant, right? Like radioactivity half-life, it's always constant. This is not the case for second order or first order. This is also a way to identify first order reactions. Sometimes that's information that they give you in the problem, that the half-life is constant. And that's a hint for you to know that it's a first order reaction. So the half-life, we can get it from the original graph, the graph of concentration over time. If we have the initial concentration to 0.1, then the half-life will be the time that it's at half at its concentration, 0.01, and it's 100 seconds, right? And what do I mean that it is constant? Yes, Harman, that is correct. If 0.05 goes again to like half of its amount, then it goes to another 100 seconds. So the half-life is constant. Each consecutive half-life will be 100 seconds. So you can get it from there, from the graph, or you can get it as Harman is stating with the formula of half-life, which is 0.693 over the value of K. Either way will give you the same answer. Okay, so now it's independent on initial concentration. Yes, Perla, it is independent on initial concentration. If you do the experiment again with a different concentration, you will have 100 seconds. Well, no. Let me think about it. Correct. It doesn't depend in initial concentration. It will always be 100 seconds regardless of the initial concentration. You're right, Perla. Okay, so we have here a summary of the integrated rate laws. I already explained the order first, and we're going to continue to order 0 and order second. But I want to show you this graph because, as we can see, all of them, the integrated rate law, all of them have the same shape as a straight line. So we can relate them all, we can all graph them and get a lot of information from the graph. So the slope of the 0 and the first will be the value of the negative k, and the slope of the second order will be k. And the half-lives, we have them here, down here, on your table that you get of constants. You have there the first order integrated rate law, so you don't have to. Well, and now this year we have the, it's going to be open notes, so you can have this chart if you want in the exam. Okay. Yes, so our recommendations is now it's open notes. You should do your own notes because the best way to learn is by doing your own notes. So you can do, I recommend you to do a cheat per unit where you place all the hints of a particular unit, like very visual. If you want to have them there at hand, separated by units, I think maybe you won't even need it, because if you do your own notes, that's an excellent way to study. And maybe you won't even look at it through the exam. But that's a really way to organize the ideas in your brain and to have it there just for you to be calm that you have it right there. So yeah, this is something that you can have in your notes for the exam. Okay, let's move on to two more examples. We have an example of second order. Well, I already told you that is second order, but we're going to do all the work. If we didn't know that this was second order, what should we do? We have the concentration. So using your graphing calculator, you can do the graph of the concentration and then move on from there. So the first question is to identify the order of reaction. Again, they're giving us one experiment with different times and different concentrations. So that should be an indication that it's an integrated rate law and we need to graph. Okay, just to recap. So we graph these values and we notice instantly that this is not a straight line. So we don't know which order is it. So we can do the natural log and we notice again that it's not a straight line. And finally, we will get the straight line with the reciprocal of the concentration. So now this is the indication that it is second order in respect with the reactant. Right? So it's second order, so that's why it has the exponent to the power of 2 on the one reactant that we have. Questions up to here? Okay, let's move on. So the value of the rate constant, remember, how did you get the value of the rate constant in these problems? Using the graph, what do we have to look for? Exactly, we have to look for the slope, correct? On the graph where you plug in the reciprocal of the concentration, again, you can do it directly with your graphing calculator, or you can do the calculations for the slope. And then if they ask you the half-life of the reaction, you use the equation for half-life, plug in the values, and careful here, well, make sure you get the correct initial concentration or the correct reciprocal of the initial concentration. And then you will get the half-life as well doing the calculations. And then, of course, you can check remember, a very good idea is to check your work. So you can go to the original graph and check your work, 0.01, half of it will be 0.005. So how much time it takes, it's here, and it makes sense, is the same as 1.63 times 10 to the negative I'm sorry, times 10 to the power of 3 seconds, so 1,600 seconds, more or less. So our answer makes sense. Any questions here? And finally, they ask us to calculate the concentration of the reactant of butadiene at a specific time. In this case, 1,500 seconds. So we use the equation, we plug in the values that we have, and remember that our from the formula it would be the reciprocal, so we need to do the reciprocal to get the concentration of A at a specific time. Okay, and then it will make sense to go to the chart again of the original values to check if your answer makes sense. Any questions with second order reactions? Okay, let's go to order zero reactions. Okay, in order zero, the rate is constant. It doesn't change with concentration as it does with first order or second order. So in rate zero, the rate will be equal to K, to the constant. So the integrated rate law would be the concentration of A equals to the negative K times T plus the concentration of the original concentration of A. And this is the formula for the half-life. So what graph do we need to plot to get a straight line? Excellent. Such brilliant students today. Excellent. Very good. Yes. Yes. Concentration of A versus time will give a straight line. Okay. Now, something that is that is very common for zero order reactions is that usually these reactions work with a catalyst. Remember that a catalyst is a substance that is neither a reactant nor a product, but helps the reaction to proceed. It usually speeds it up. So in this case, it's usually a metal surface or an enzyme. Most biological processes that take place in our body use enzymes. So most of the reactions in our body are zero order reactions. It has a lot of implications in biology and biological systems. So for example, an example for this type of catalyst. If you have this reaction where dinitrogen oxide decomposes into nitrogen and oxygen, this reaction takes place in the presence of platinum metal. When all the binding sites of the metal are occupied, then the rate becomes constant. I made some diagrams here, and for example, of course, the rate is going to change until you have all the platinum used up. Once the platinum is all occupied, then the rate will be the same regardless of the quantity. It doesn't matter if you have more reactant, the rate will be the same because the only reaction that is occurring is the reaction is where it is in touch with the catalyst. Does this make sense? In biology, the catalyst is usually like it has to do with a lot of shape in biology. It has to enter the enzyme with a specific shape, and then the reaction will take place until the enzyme lets go of the products. So that's why it's independent of the concentration of reactants. So for example, they are not nightmares. I'm sure you learned a lot in AP Bio. It has a lot of implications in life and in health. So, okay, let's move on. So, for example, the decomposition of ethanol sample, 1.20 molarity, they're giving us the initial concentration. On an aluminum surface, that's also a hint that this is a metal surface, so it should be a hint that is a zero order reaction. Was studied at a constant temperature. So you have there the reaction, and they're telling you this time they didn't make you do the graph, because they are telling you that the plot of the data collected of the concentration versus time resulted in a straight line. They're already telling you that that's the straight line. So that's a hint that it is zero order. One hint, another hint. Okay, and you have there the slope. It says determine the rate law and the integrated rate law, determine the value of the rate constant, and calculate the half-life for the reaction. What would be the rate law? The correct rate will equal to K. Yes, it's okay, Carmen. That's right, K, because the one that you said was first order, and this is zero order. Correct. Excellent. So K, correct. And what would be the value of K? What would, exactly, the slope, the positive slope, right? Because it's correct, correct. And for the half-life, we use the correct. Yes, that's something that you must remember. K, it's always positive. If the slope is negative, then you change it to positive. Yes. Well, we're going to see in a moment in the, okay. Then the half-life, so if we go again to A, yes, we have the rate law equals K, and the integrated rate law is the one considering the concentration of ethanol. And then the value of K, we already mentioned that it was the slope, correct? The positive slope, correct? And the half-life, we are going to use the formula and substitute in the formula, and that's how we get the half-life. Any questions in here? Okay, Anika, in the next slide. The constant is always positive, yes. The constant is always positive, even though the slope is sometimes negative. And okay, here we have it. Here we have the summary. So we have again the rate laws for zero, first, and second order. We have the integrated rate law. We have how we're going to get a straight line. We have the rate constant, right? So for zero and first order, our slope is going to be negative, so we make it positive. And our second order, our slope is going to be positive from the start. But yes, our K, it's always positive. And then here we have the formulas of the half-life. So the way that these graphs are going to look like is like this. So yes, remember order zero, the concentration, it makes sense to have a negative slope because the concentration is decreasing over time. But our K, it's positive. And then the natural log will also give us a negative slope, but the K is positive, so we turn it to positive. But of course, the reciprocal of the concentration, it makes sense that it will give us a positive slope. So now it would be directly the K, the slope. But that's it. If you have any questions, here is my email. If you have a specific problem that you're having questions to solve, I will gladly help you if you have any other doubts. Questions up to here?